Welcome to Chapter 2, Section 1. We get to start discussing derivatives, and that's going to be exciting and a very foundational piece to our studies the rest of the year. So I want to make sure you get these down. Section 1 is the mathematical definition of derivative and how do you calculate it, and then later in the chapter we learn some shortcuts. So bear through section 1 and it will get better and a little bit easier. So day 1, let's just find the slope of the tangent line to a curve at a point. So hopefully you're recognizing the word tangent line from geometry and the word slope from algebra. We'll tie those two together. And then we're going to use a limit to help us define how to calculate a derivative. So all these things will tie together nicely. Derivatives are all about change, and they're also all about slopes. So there you can kind of fill in that top blank. It's all about change or slopes. They show how fast something is changing, which will refer to the rate of change at any point. And what's interesting is we're talking about a rate of change at a point, and that's different than what you've been taught in the past. The derivative gives the slope of the curve at a point. It's also sometimes referred to as the difference quotient. Another place for you to fill in your blanks there. And I'll give you just kind of a little picture to start out with. We know what a tangent line is. This is an example of a tangent line right here, isn't it? Where it's striking the curve at a single point, and it's almost like skimming by, isn't it? It's skimming by that curve and just barely touching it at that one spot. Okay, so that's what a tangent line is all about. What we'd like to be able to do is give the exact slope of this tangent line at that particular point. But that brings up some interesting problems, doesn't it? Because what we've been taught in the past, let me get rid of that, is that a slope is calculated. Remember how we used m to signify slope? We've always been taught it's y2 minus y1 over x2 minus x sub 1. Or if you wanted to think of it, it's the function evaluated at x2 minus the function evaluated at x sub 1 divided by x sub 2 minus x sub 1. Those are definitions that we have used to calculate slope. But notice how this requires 2 points. We need 2 ordered pairs in order to do that calculation. And now what I'm asking you is, how about just taking 1 ordered pair? Let's say we've got x, y point here. What's the slope for the tangent line at that point? And that's where you're like, huh? Well, there's a neat way to think of this. The slope of the secant line. Now, if we talk about secant line, do you remember what a secant was? A secant is a line that goes through 2 points. The slope of the secant line can be calculated using, that's supposed to flip over and say 2. I'll put it in there for us. The secant line will use 2 points, which is what we're so used to. We're used to doing the slope of the secant line. Now what we're going to do is let's change it up and let's make it the slope of the at a point, the slope of the tangent line. So I can kind of envision, I want to take the slope, maybe I want to take the slope at P here, and I'm going to try and get this so it somewhat just skims by on P, and that's not too bad of representation. What would its slope be? Well, the notion is we're going to take this point Q and just bring it closer and closer and closer to P, and I still have 2 points, don't I? But I want to get P and Q so close that it resembles the tangent line then. All right, so let's start off with this picture where we're going through P and Q. Okay, so go ahead and draw that in on your picture. We're going to turn this secant line into a triangle, basically. So there's this point x, and when I put it into the function, I get out some y value, and we create this point here, x1 and maybe f of x1. Then I'm going to put this q out here some distance away from x. So there's going to be a distance sitting in between here. And I'm going to move it over by h, or some value called h. Well, that'll give me a place here of x plus h. So say this had been 3, and I moved it over, maybe I let h be 2, so I'd be now at 3 plus 2, or 5, right? Bring this over, here's my height of f evaluated at x plus h. Well, in calculus, what we're going to do is we're going to take this h value down, and we're going to shrink it down, 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 and bring this closer in to x. As a matter of fact, we're going to let h go down to next to nothing so that I bring this point almost right in on top of x. So that will bring q, that'll force q to come down next to it too. And I'll bring the q part down with it. So here's where we're at now. Well, if I draw a line through these 2 points now, boy, we're getting closer and closer to this actual tangent line slope. And that is what we are all about. So the slope of the tangent line is also referred to the average rate of change. What we're going to go after is the slope of the tangent line instead of the secant line. The derivative of a function is noted by f prime of x. So that's the notation for the mathematical notation for derivative. And what is the calculation for it? Well, notice we've got this word limit in front, and we're going to let h go down to 0. So think about that previous picture that we were drawing when we allowed the x plus h value to come close to the x value. And here is the limit definition. We're going to take f of x plus h minus f of x, all divided by h. And you can kind of see here's the 1 point, f of x, minus the other y values at that point x. I would have x plus h was the x value minus the other x value. And here's where x minus x goes away, and we end up with just h on the bottom. Okay, so what we really was from a slope definition that we were used to that creates this limit of a slope. F prime of a equals slope. It's the slope of the tangent line at some point referred to as a. So f prime of a will be the actual slope when x is a. An alternate definition when I'm at this point a is f prime of a equals, and you may, oh, this one is provided to you, f of x minus f of a over x minus a. But notice what's happening here on this limit too. So if I have x and I have some value of a, it's saying let x, I wish I could just grab x, let x move over and become real close to a, and we'll have the slope of a tangent line instead of a secant line. Moving on, let's actually try one. So here's a nice simple starting one. Use the definition of derivative to find the slope of the graph. And here's our definition of the derivative, which also looks like the slope of the tangent line, and or we could write it as f prime of x. So let's sketch the graph. We're at 3x minus 2. So we come down to 1, 2, 3, 4. So I'm going to start by plotting my y-intercept at -2, and then I'm going to move up 3, 1, 2, 3, and over by 1. So we get a slope of 3 for this. And this will be y equals 3x minus 2. There's our graph. We want to find f prime of 3, or the slope when we are at -3. 1, 2, 3. Here's my -3. And if I come down, intersect with my graph here, I need to extend, intersect with my graph. What is the slope at this point? Well, on this one, it's kind of obvious, right? It's a linear function. We know the slope is -3. Or, I'm sorry, +3. The slope is +3. Sketch the graph. Let's find f prime of x. We're going to use that limit definition. So the limit as h goes to 0 of f of x plus h minus f of x, this is one of those that you'll have to memorize, all over h. Plugging stuff in, I'll give us the next line, write the word limit as h heads to 0. Now I need to evaluate my function at x plus h. So I take and plug in for my x, I plug in x plus h. And then I got a -2 because that's what the function says to do. Then I do minus, now f of x, that will look like 3x minus 2 because I'm evaluating it just at x, all over h. Now it's just a matter of doing the math. So the next line will look like the limit as h heads to 0, distribute 3x plus 3h minus 2, this I should have had in parentheses, minus 3x plus 2 all over h. Simplify, 3x cancels with the -3x to make 0. -2 plus a 2 gives us 0. And I'm left with the limit as h goes to 0 of 3h over h. Cancel your h's because I couldn't substitute 0 in. And now I get a final answer of 3. The derivative f prime of x is equal to, and I could have this all the way down here, f prime of x equals 3. So what it's telling me is the derivative is 3. And when I'm at -3, it's also going to be 3 there. All right, find the slope of the tangent line to the graph of the function at the given point. And here we have a quadratic, so a little bit more interesting, and the picture is provided to you. We want to look at what the slope will be at 2. So 1, 2, let's figure out if we put in 2, we're going to be up in this region. Draw in a tangent line. Tangent line would look something like that there. And my question is to you is, what is the slope? What is the slope when x is equal to 2? Or in other words, what is f prime of 2? That is the big question. So first off, let's evaluate the general derivative. So step 1, f prime of x will equal the limit as h heads to 0. We're using this over here, that formula. I need to evaluate f at x plus h. So wherever I have an x, I'm going to insert x plus h. Okay, there's my first one. So x plus h goes in here, and then it gets squared because of the squaring there. And then 4, I put in x plus h for that x, and we subtract 1. That took care of just this portion. Now subtract the actual function evaluated at x, and that is what this represents. That is our function at f of x. So subtract. I'm going to use a parenthesis because I'll have to distribute x squared plus 4x minus 1. I'll have to distribute that negative all over h. Now it's just the math of it. So we have the limit as h goes to 0. We got to square this thing, and if you're good at squaring, it won't be hard work at all. Think of it as x plus h times x plus h, FOIL it out. Plus 4x plus 4h minus 1. Now take your negative. This is a step that I bet Half the people will mess up on the test because they'll forget to distribute this subtraction sign through all over H. Simplify this out. So look for things that are in common, right? Or opposites. I've got an positive x squared and a negative x squared. I've got a positive 4x and a negative 4x. I got a negative 1 and a positive 1, all adding up to 0. What I have left, I'm going to rewrite my next line just so I can see what's still left and make it more obvious to you. I've got 2xh plus an h squared plus a 4h all over h. Well, if I tried to substitute 0 into my limit to solve it, I immediately see I get 0 on the bottom. But the nice thing is, and this is what you're going to want to have happen, is that they all have an h in common. So the limit, as h heads to 0, let's GCF out that h. And that gives us 2x plus an h plus a 4 all over h. I just simply GCF'd. Now, h cancels h, and I no longer have an issue with substituting 0 in, do I? I'm now at the stage where I have the limit as h goes to 0 of 2x plus h plus 4. And if I tuck 0 in here, substitute it in, I get 2x, because I'm substituting h, I'm not substituting x, plus 0 plus 4. So this simplifies to 2x plus 4. We just figured out, if I bring this on down, I just figured out that f prime of x is equal to 2x plus 4. Okay, that took care of part 1 of our problem. Next thing it wanted to know is what the slope is at 2. What is the derivative at 2? Well, that means simply let's plug in 2. So here's part 2 of our problem. Part 2. F prime of 2 equals, well, we're going to do 2 times something plus 4. I'm going to put in, instead of this x, I'm evaluating it 2. 2 times 2 is 4. 4 plus 4 is 8. I know that the slope at 2 is 8. When x is 2, and you come back up to our picture here. So what we just found out is that f prime of 2 equals 8. That describes the slope of this tangent line. And then it says, find a point on f of x at which the tangent line is horizontal. Well, the horizontal will happen right down here, won't it? There's a horizontal place. Where does that occur? Well, what we're going to do is use our, this is step 3, finding the horizontal. Find horizontal tangent line. So I'm going to take f prime of x and set it equal to 0 because I want to know the slope. Remember, this is slope. I want to find out when the slope is equal to 0 for a horizontal line because that describes the slope of a horizontal line. So I'm going to take and substitute for f prime. I'm going to go 2x plus 4 must equal 0. And then 2x equals negative 4. Therefore, x divide by 2, and we're at negative 2. A horizontal line, a horizontal tangent line, occurs at x equals negative 2. Does that look about right for our picture? Well, this is over by 1, 2. This is negative 2. Boom. The tangent line through that point, x equals negative 2, is horizontal. I do believe that that probably is enough for tonight, and I will do C and D in class, so we'll get a little bit of lecture in class too. Thanks for hanging in there.